Alright, go.
Whose Fault Is It? By Julian and Lachlan. In the outline situation of a T-bone crash, we have two vehicles evident, a 1,363 kilogram Audi and a 1,535 kilogram Mitsubishi, colliding in an intersection between Ballarat Road and Holloway Court. At point A, it shows the start of the crash, with point B being the initial site of impact, and point C showing before the impact of the crash. The Mitsubishi driver claims that the Audi driver was at fault, pulling out into the intersection on a red light, where the Audi driver claims the Mitsubishi driver was at fault because he jumped a red light. The Audi was traveling in a Y direction and Mitsubishi in X direction on an axis, with 24 degrees from the skin marks, showing 3.2 meters from the impact. Yep.
First we will need to find the friction. Done. We can find this by the indication of the skin marks. The friction is the force what is making the vehicle slow down. So first we need to find the coefficient of the kinetic friction. By using this chart on the right, we're able to get the force done by kinetic friction. As we can see in this chart, the force of kinetic friction starts at 70 newtons. So that will be our kinetic friction. And the mass, so that'll be over the mass of the 10 kilogram tire block, will be 10 times gravity. We're using this because it is the same friction force as both the tires of both the vehicles. And if we put it into the formula to find the coefficient of kinetic friction, that should be 0.71 is the coefficient. Next, we need to find the total weight of both the cars and their drivers. We just add up the mass of the Mitsubishi plus the mass of the Audi plus the driver of the Mitsubishi plus the mass of the Audi times the gravity. That will give us the total weight of the vehicles of 29,958.6 newtons. Now we need to find the kinetic friction of the drivers and their vehicles. So that's just the coefficient of kinetic energy times the mass of the drivers and their vehicles to get the force done by kinetic friction in this collision. Adding the numbers into the formula, we should be able to get the force done by kinetic friction is 20,971 newtons. The velocity just after the crash, it's time to find the velocity just after the crash. Okay, now we have the kinetic friction force, we can find the work done by kinetic friction, and this will help us find the initial velocity just after the crash. So the work done by kinetic friction is equal to the force done by kinetic friction times the distance traveled from the start of the crash to the end of the crash. We've got the force done by kinetic friction in the last slide. So if we just punch in the numbers, we should be able to get 67,107.2 joules. Finding the initial velocity, we need to integrate it with the final to the initial of the kinetic energies. We know the final velocity in this car crash is 0 because the cars are not moving, so we don't need to worry about that. It will be all done by the start of the crash, the initial start of the crash. So that's one half times the mass of the vehicles times the initial velocity squared will give us the work. Rearrange that to get the initial velocity done in this car crash. So it'll be 2 times the work done over the mass square root will give us the initial velocity. Punching in numbers, we should be able to get 6.6 meters squared, 6.6 meters per second. The speed of the two cars, it was the elastic collision, so we're able to use this formula, was the mass of the Mitsubishi times the initial velocity of the Mitsubishi plus the mass of the Audi times the initial velocity of the Audi equal to the mass of the Mitsubishi plus the mass of the Audi is the final velocity. In this one, the final velocity is the initial velocity we found in the last slide because we're looking at before the crash. And this is the speed of the cars before the crash. This is the speed of the cars at the start of the crash. So we know the final velocity, but now it's time to find the speed of the Audi, as they claim they were not speeding at all or don't have a velocity at all. So that'll be the mass of the Audi times the velocity of the initial initial velocity of the Audi is equal to the mass of the Mitsubishi plus the mass of the Audi is equal to the final velocity sine theta. Rearranging that to that the initial velocity of the Audi is equal to the mass of the Mitsubishi plus the mass of the Audi times the final velocity sine theta over the mass of the Audi. Putting in our numbers, we will be able to set the 5.67 meters per second is the initial velocity of the vehicle. Converting that into kilometers per hour, we can see that the vehicle was traveling 20.41 meters kilometers per hour. So the Audi is at fault because he pulled out in front of the vehicle, as he claims he wasn't moving at all and was sitting in the middle of the intersection. Now we need to find out if it's possibility that Mitsubishi was speeding for this collision. So that's the Mitsubishi. The mass of the Mitsubishi times the initial velocity of the Mitsubishi is equal to the mass of the Mitsubishi plus the mass of the Audi is equal times the final velocity cos theta. This is going in the x direction. So rearrange that to the initial velocity of the Mitsubishi is equal to the mass of the Mitsubishi plus the mass of the Audi times the final velocity cos theta over the mass of the Mitsubishi. Putting in our numbers, we are able to see that the speed of the final initial velocity of the Mitsubishi is 11.45 meters per second. Converting that into kilometers per hour, we can see that it's 41.24 kilometers per hour. So the Mitsubishi wasn't speeding for this collision. So the Mitsubishi was going the speed limit, and the Audi was pulled out in front of it. All right, collusion.
In concluding this crash, using both elastic formulas and work formulas, we are able to get the outcome that the Audi was at fault, pulling out into intersection on a red light. Thank you for listening.
Thank you.